Hello and welcome to our lesson on special rational functions. So I have titled this lesson Special Rational Functions, but in reality the rational functions we're going to look at aren't any more special than the others. I just call them special in that they don't behave how, let's say, the parent rational function behaves, where you have a vertical asymptote, you have a horizontal asymptote, and then you have your branches, right? Or maybe you have a couple vertical asymptotes and then branches in between, and left and right. The rational functions we're going to look at today have possibly other types of asymptotes and also what we call removable discontinuities. Okay, so just to recap, if we are going to find vertical or horizontal asymptotes, vertical, in my opinion, the easiest to find. We know that the vertical asymptotes are going to happen when we have restricted x values. Those would be values of x that would make the denominator equal to 0. Those are undefined. Vertical asymptotes will happen there. Then we said horizontal asymptotes are going to occur in two cases. They are going to occur at the x-axis, which is where y is equal to 0. If our function values are approaching 0, that will happen because the degree of the numerator is less than the degree of the denominator. Like our parent function, if I have something like 1 over x, as this gets really large, the value of my fraction gets really small and approaches 0. So anytime that relationship happens, again, the bottom is going to increase faster than the top, you're going to have a horizontal asymptote at the x-axis, which is where y is equal to 0. Now, if the degree of the numerator and denominators are the same, so if those degrees are equal, I showed you how you can just find the quotient of the two polynomials, and the actual quotient shows the shift for the horizontal asymptote. So at the quotient of the leading coefficients, you can find the horizontal asymptote when those degrees are equal. So the horizontal asymptotes will occur at the quotient of the leading coefficients if the degrees are equal. I put if the in there twice. I'm like, what does that look funny? Don't mind the typo. Okay, now, what if, or what happens when, the degree of the numerator is greater than the degree of the denominator? Because those would be the three cases when you're comparing degrees. We said, well, if the top is less, it's going to be at the x-axis. If the top and the bottom are equal, we're going to find the quotient of the leading coefficients. If the top is bigger, greater than the bottom, then there will not be a horizontal asymptote. Because if the top of our fraction has a higher degree, so we have something like x to the third over x squared, for example, as we increase the values of x, the top is going to grow faster than the bottom. So that means as x gets infinitely large, y gets infinitely large as well. So these values continue to increase as x gets bigger. And so that increase means we're going to be headed up toward infinity, or if there were negatives, down toward negative infinity, but no horizontal asymptote. Now, there are other types of asymptotes that can happen. And just like with these, when the quotient, or when the degrees were equal, I said find the quotient. You can see where the horizontal is. That's what we're going to do here. We're going to find the quotient of our rational function. We'll actually take the numerator and divide it by the denominator to rewrite our function, and then I'm hoping it will become clear where this new type of asymptote will happen. It won't be horizontal, but again, it should make it clear where it's going to happen. So to see what we know it's not going to be horizontal, to see what will happen, we're going to use division to try to rewrite our function. Okay, so starting with this one, and I already made the picture here, so I'm hoping you can kind of see and remember from college algebra what's happening in this picture. But here's the function that's in this picture. Okay, if I was to actually find the quotient, take this numerator, divide it by this denominator, I can use synthetic division to do that. So I'm going to have my 0 outside of the box. The 0 for the denominator would be 2. And in my box, the coefficient of x squared, coefficient of x, and my constant. So I bring this down. 2 times 1 is going to make 2, and then I add to get 4. 2 times 4 is going to make 8, and then I add to get 3. So this, remember, was an x squared. I divided by an x to the first, which means now this is going to be an x to the first. And this is my constant, and this is my remainder. So I can take my function and rewrite it. Now I could say y is equal to 1x plus my constant of 4 plus my remainder of 3 over my divisor, which was x minus 2. So I've just rewritten this as its quotient and remainder, okay? Now this form is a little more helpful because this part is a transformation of my parent function. I know what's going to happen to this part of my fraction. As x gets infinitely large, this fraction will approach 0. It's going to zero out, it's going to go away, so all that's going to be left is what we have out here. Now, when we did this when the degrees were equal, we had just a constant, and so that was the constant value for the ends to approach, the horizontal asymptote again. But now, instead of a horizontal asymptote, we have this whole linear function, and that becomes our new asymptote. So in fact, if I was to graph the line y or equals x plus 4, I would be crossing the x-axis at, come on pen, at 4, and I'd have a slope of 1, and this is the equation for that line. This is the asymptote in that graph. That is the place that the ends are approaching. So look at the left end of this graph. It's going to get closer and closer to that line. Look at the right end of the graph. It's going to get closer and closer to that line. So we have in here a linear equation for our asymptote instead of a constant, a horizontal asymptote. And in an asymptote like this slanted line is called an oblique asymptote or a slant asymptote. So that is a slanted or oblique asymptote. And the vertical is exactly where we would expect it to be. I know that my restricted x value is 2. That's what I put out here. And so at x equals 2, there is our vertical. So the picture now hopefully makes a little bit of sense. If I divide my functions, I can see where the asymptote's going to happen. So when my degree of my numerator is exactly 1 more than my denominator, like we have here, that slanted asymptote should happen every time. So every time I divide, again, like a degree of 2 by a degree of 1, I'm going to have this degree of 1 left over. Or if I took a degree of 3 and divided by a degree of 2, I would have a degree of 1 left over. I would have something linear left over, or as my quotient actually. And so you'll see that slant asymptote happen every time that is the case. So these happen when we know when the degree is top, or the top is bigger than the bottom, there's not going to be a horizontal. When the degree of the top is exactly 1 more than the bottom, it's a slanted asymptote. Okay, but you don't have to commit that to memory. You just divide the function to see what it looks like, and the behavior becomes clear. Here's the parent form that's going to approach 0 that still has that vertical at 2, and here is the slanted asymptote instead of the horizontal. Okay, so let's try another one. Notice in this one the degree of the numerator is 2 more than the degree of the denominator. So it's still bigger on the top, which means there isn't a horizontal. But look at this picture. It looks pretty crazy if you ask me. I don't know if you've seen these. I definitely don't show these in college algebra. But to try to understand what's happening, again, I'm going to just divide my functions. So I'm going to take my 0, negative 5, and divide it into the numerator here. So I have my coefficient of x cubed, x squared, x to the first, and then my constant. I'm going to bring this down, and then negative 5 times 1 is negative 5. Add, I get 0. Multiply, add, multiply, add. And what do I have left over? Remember, this was an x cubed, and I divided out an x to the first, so this is going to be an x squared. I'm not going to have an x to the first term, but this is my constant, and this is my remainder. So now I can rewrite my function. It's going to be rewritten as 1x squared minus 3 plus my remainder of 1 over my divisor, which was x plus 5. Now again, this part of the fraction, this is my parent function, right? There's my parent rational function. I know that that fraction is going to end up, as x gets bigger, approaching 0. And so if this fraction is going to go away, all we're concerned with for our outputs is what's left over. And this leftover piece becomes a new asymptote for us. Instead of having a line out there that our ends approach, instead of having a constant out there that our ends approach, we have a parabola that our ends are going to approach. And in fact, if we were to graph that parabola, we're going to see it. So let me just highlight this for you. This parabola, x squared minus 3, would cross the x-axis down here at 3. And this is what is guiding the behaviors here. So we're going to see both of the ends approaching this parabola. And so we can have a parabolic asymptote, we can have a linear asymptote, we can have a horizontal, we can have a vertical. All kinds of weird things can happen in terms of asymptotes. Now the vertical hasn't changed. The restricted x value here is still -5, right? Still -5 here. And so at -5, if I put that vertical in, there it is. I can see again, oh man, I drew my parabolic one incorrectly. Let me just fix this. This one. Parabola is going to go out here like this. The ends, right, have to approach the parabola. So instead of the ends approaching a horizontal, instead of the ends approaching a line, the ends are approaching the parabola. So this end gets closer to the parabola, this end gets closer to the parabola. And again, the vertical, not changing. We still have a vertical asymptote at x equals -5, and that's what you see happening inside, right? The ends are approaching the parabola, but the inner pieces of the graph are approaching that vertical. So really strange, and I'm not going to require that you actually produce any graphs like this one just because it's so unfamiliar. You should definitely be able to graph one of these, but when you divide the function, again, the behavior or where the asymptotes are hopefully becomes a little more clear. So this ends up being a parabolic asymptote. Okay, so that's the concept. Let's try to graph one on our own. So if I was looking at this function and I just said to graph it, I would first probably look for the vertical asymptote because I think those ones are pretty easy. What's going to make our denominator equal 0 is going to be a -6. So I'm going to go ahead and go to my graph over here, go to -6, and make my vertical asymptote through that x value. Okay? And then I might look for a horizontal asymptote, but now I can see that the degree of the top is bigger than the degree of the bottom, which means this thing is not going to have a horizontal asymptote. So to see what it is going to have, I'm going to divide it. So I'm going to take my -6 and divide it into my 2, 13, and 4. Bring this down. Multiply, I get -12, add, I get 1. Multiply, I get -6, add, I get -2. That means I can rewrite my function. Y can be rewritten as, remember this was, let me go to pink. This was an x squared. I divided an x to the first, so this is an x to the first, and this is my constant, and this is my remainder. So this function gets rewritten rewritten as 2x plus 1 minus my remainder of 2 over my divisor x plus 6. Now I'm going to move this because I can. And I can see now here is where my asymptote is. Instead of my asymptote being at a constant, instead of it being some horizontal asymptote, that is an equation of a line. That's a linear, slanted, oblique asymptote. So I'm going to call this an oblique asymptote. And I'm going to say it is at y equals 2x plus 1. And actually, I'm going to do this again in a different color so you can see it differently on the graph. So I'm going to say this is an oblique asymptote at y equals 2x plus 1. Okay? So if I need to graph that line, y equals 2x plus 1, it's going to cross the y-axis at 1 and have a slope of 2. So up 2 over 1, and I can make another point. As many of those as I need, but that should be fine here. So I'm going to make this slanted asymptote like this. Okay? Now I just need to figure out where my branches are. So kind of like with the parent, I have like 4 quadrants here, right? I have this area, I have this area, I have this area, this area. I'm going to have one branch to the left and one branch to the right of the vertical. So the first branch could be up here or down here, one or the other. And then the second branch could be up here or down here, one or the other. So to figure out where the branches are going to go, I'm just going to make a table of values, and that should be sufficient for us. So I'm going to plug into my table again something to the left and something to the right of my vertical asymptote. So I think to the right, 0 is always a nice number to plug in. So I'm going to go ahead and do that. If I plug 0 in, everything with an x is going to go away. I'm going to be left with 4/6 or 2/3. So if at 0, my function is up here at 2/3, that's definitely below my intercept of 1 there. I know that my branch has to be in this quadrant here. It's got to be in here because the end has to approach that oblique at the end, and then in the middle I have to approach the vertical asymptote. So I'm going to go ahead and sketch my branch approaching this oblique and approaching this vertical. So it's going to be a really wide looking branch, okay, something like that. And then I need to pick something on the other side. So now I know I won't have anything happening in here, because if I did, then we wouldn't be a function, we wouldn't pass the vertical line test. So the other branch, is it going to be up here, or is it going to be down here? Most likely they're opposites of one another, like most likely case is going to be here, but just to be safe, let's plug in an input, again, to the left of my vertical asymptote. So maybe I plug in like a -7, for instance. So let's put -7 in. Alright, this will be a fun one. 2 times -7 squared plus 13 times -7 plus 4, all divided by -7 plus 6. And that ends up being a whole bunch. I'm going to just have my calculator. I do not have my calculator. Oh, Lord. Okay. Calculator. Thank you, calculator. Alright, so make a fraction on the top. 2 times 49, and then plus 13 times -7, and then plus 4, and that's divided by -1. I don't need to do that. So I get a -81. So at -7, my graph is way down here at negative. Did I put that in right? I feel like I missed something. I feel like that branch shouldn't be there. What did I do? 2 times 13 times... Oh, I put a 3 in there instead of a 13. Goodness, -11. That sounds better to me. Okay, you were probably, I'm hoping, screaming at me. -11. Okay, so at -7, my graph is at -11, which is going to be just inside of that boundary. And so again, I'm going to have a branch that's in this area that I thought it was going to be. And if you just weren't sure, because maybe you're like, oh, I didn't draw my line accurately enough, you could always pick another x value, like pick -8 or pick something else and make sure it's in there. Okay, and so I'm going to sketch my branch in. Again, it's got to approach the vertical on the inside here, and it has to approach the oblique on the end. So something like this. And it's just a sketch so we understand the behaviors at the ends and in the middle, where we approach the asymptotes from both directions. Okay? So we know how to find horizontal, we know how to find vertical, and now if we don't have a horizontal, we know how to find what could possibly happen using division. Alright, the other special case I want to talk about is when we have what we call a removable discontinuity. So sometimes we have a rational function that can be simplified. Like if the top and the bottom are factorable and something reduces out, if that function simplifies, if the equation simplifies, the graph is going to be simplified too. So if a rational function can be reduced or simplified, its graph is going to be simplified too. Now, what happens when a factor is reduced out is an x value that was restricted, that gets reduced out. Well, those restricted x values normally cause vertical asymptotes, so a vertical asymptote sort of gets removed from the picture. And a vertical asymptote is a discontinuity in the graph. So when this happens, we call it a removable discontinuity, right? The vertical asymptote, a discontinuity, is removed from our graph when that restricted x value gets reduced out of the equation. Now, the restricted x value is still a restricted x value. It's still restricted from the original function, so we still have to account for it in some way. It just doesn't affect the behavior of the new function, the simplified version, in the same way it would have had it stayed in. And so to show in the new graph that that x value is restricted, we make a hole in the graph. So a hole is placed or created in the graph at the removed discontinuity because the x value is still restricted from the original function. It just doesn't make an asymptote anymore because we simplified it out, we reduced it out. Alright, so for instance, I have a couple, again, graphs are already created just so we can try to understand, wrap our brains around what's happening, or maybe just review because you have seen this in college algebra. So if I look at this function, maybe at first glance it doesn't look any different from any of the others, but in fact it is. My vertical asymptote, right, should have been at -1, but notice my graph doesn't have a vertical asymptote at -1 because the top of my fraction is factorable. If I factor the top, the factors of 2 that make 3 are 2 and 1, so the top is going to factor into an x plus 2 and an x plus 1. And if I have a matching x plus 1 in my denominator, those cancel out. They reduce from my function. So what's left is y equals x plus 2. Why did I say x plus 2 and write just a 2? I don't know. So this is the graph, the simplified form of the function. That's the graph we see here. That is the line y equals x plus 2. But notice, I have a hole in my graph. So instead of having a vertical asymptote at x equals -1, right, that's the restriction. X cannot equal -1. There should have been a vertical asymptote there, but because it simplifies out of the function, right, it doesn't create that vertical asymptote anymore. Our function is simplified, the equation is simplified, the graph is simplified, but we still want to make a hole in the graph at that restricted x value to say, hey, this was restricted from the original function. Okay, so the removable discontinuity, the asymptote is removed and a hole is put in instead. So again, that restriction that got reduced out, that is the hole in the graph. Now, if I wanted to figure out, now I can see it on the line, but if I wanted to figure out where this y value is, what's the coordinate for y in that point, I would have to plug my x value into my simplified function. So this would be the graph I'm trying to create. If I plug -1 in, that restricted x value, -1 plus 2, I get +1. And again, that's the output here. Okay, so if we want to find the coordinates of the hole, we take our restriction and plug it into our new function, our simplified function, because that's the point we're trying to find on that graph anyway. Okay, so hopefully that makes sense. I'm going to show you another one. This function ends up being linear when it's simplified, but they don't all work out that way. For instance, here, this still looks like a rational function, but again, it's got a hole in it. So let's try to see what's happening. This time the denominator is factorable. Factors of 10 that make 7 are going to be 5 and 2. So if I rewrote my function here, y equals x plus 5 over x plus 5 and x plus 2. Now I would have anticipated two vertical asymptotes in this graph, one at -5 and one at -2, because there are two restricted x values there. But what happens is this one gets reduced out of the function, out of the equation, which means that vertical asymptote is no longer in my graph. Okay, all that I'm going to see on the graph is the simplified function, which is 1 over x plus 2. So 1 over x plus 2 still has a vertical asymptote at -2. And I see that in my picture. Vertical asymptote at -2. And this is not shifted up or down, so it should have a horizontal asymptote at y equals 0. So y equals 0, horizontal asymptote, right? This restriction got reduced out, right? So it no longer impacts my function in that it does not make an asymptote, but this restriction still has to be accounted for. So right here is where we account for it. So in this restriction that gets reduced out, we know that x cannot equal -5. Again, it just doesn't create an asymptote anymore. So we create this hole in the graph there at that x value of -5 to say, hey, this x value was restricted, but because it reduced out, it doesn't create an asymptote anymore. All right. Now, again, this y value that corresponds with that x value, we would get by plugging into our simplified function. If I plugged into my function 1 over that restricted x value, -5 plus 2, I would get -1/3, and that's precisely what I see here, -0.3 repeating. Okay? So that's the idea. Let's try to graph a couple ourselves. For example, number 3. I know my vertical asymptote, that's the easy one to find, but I want to try to factor in my numerator. And in general, this is what you're going to want to do with any rational function as you approach it. You're not going to know if something's going to simplify if you don't first try to simplify. So you should always be trying to factor if that's a possibility to see if anything reduces. If it does, then your function, your graph, it's all going to reduce. Okay? So the top of this one's going to factor. Obviously, it's in this section of notes. 2 times 15 here makes 30. And factors of 30 that make negative 11 are negative 6 and 5. Dividing by 2 and then reducing, I see my function becomes a 2x minus 5 times x minus 3 over x minus 3. So again, I would have expected a vertical asymptote at 3, but that x minus 3 is going to reduce out. So the simplified graph, what I'm actually going to graph is just this line. That's what my graph should look like, y equals 2x minus 5. So I'm going to go ahead and graph that line, y equals 2x minus 5. It's going to cross the y-axis at negative 5. Slope of 2 means up to, right, 1. I could make another point, and as many as you need, right, to connect the dots there. So this is what that line should... That was terrible. Try to draw a straight line. Maybe? Okay, that's pretty close. This is what the graph should look like. If you put it into your calculator, that's what you would see. The only thing we have to be careful of is make sure we do account for that removed discontinuity. So the 3 does not make a vertical asymptote, but there should be a hole in the graph there. So here I know, again, that x cannot equal positive 3. So there should be a hole at positive 3. Now, how do I get the y value here? I have to input 3 into my function. So to get the... Let me change colors. To get the y value that goes here, I'm going to plug 3 into my function. I'm looking for a point on this graph, and I know the x value in that point is positive 3. So if I plug 3 in, 2 times 3 would be 6, and 6 minus 5 would be positive 1. So 3, 1 is where I should have a hole, and it makes sense on this line. There's a point at 3, 1. So I'm just going to edit my graph a little bit here. Make sure. Alright, so at 3, 1, I should have a hole in this graph. And then the rest of it is a nice continuous line. So at 3, 1, we have that removable discontinuity. Okay? Not so bad, especially if the simplified function is linear, but often our simplified function is still rational. So let's look at one more example here. Again, I'm going to try to factor the bottom. Factors of negative 24 that make negative 2 are going to be negative 6 and 4. And so this function becomes y equals x plus 4 over x minus 6 and x plus 4. And so the x plus 4 cancels out. So all I need to graph now is this reduced function, this simplified one. So y equals 1 over x minus 6. That's what I have to graph. Now I know when I'm looking at this that my vertical asymptote is going to be at x equals 6. And this is just a transformation of my parent, right? So it's gone to the right 6. It's not going up or down. So I know my horizontal asymptote is going to be at y equals 0. And so I'm going to make my vertical at x equals 6. I'm going to make my horizontal at y equals 0. And again, this is just a transformation of my parent, so I don't need to make a table to know where my branches are. This isn't reflecting, so my branches should be in these top corners. So I should have a branch of my graph here, and I should have a branch of my graph somewhere here. Alright, so there's a pretty good picture. The only thing I have to do now is remember to include the removed discontinuity. So we had 2 restricted x values. The only one that's left in the function is 6. That's why that's the only one that I see in my picture. But here, remember, what color can I use? Pink. Here, right, we still know x still can't be negative 4. It just doesn't create an asymptote anymore like this creates the asymptote at 6. So there's going to be a hole in our graph at that x value, negative 4, and I need to find the y value that goes with it. So I'm looking for a point on this graph. I'm going to plug negative 4 into that function. So I would have 1 over negative 4 minus 6, which would be a negative 1/10. So a negative 1/10. So at negative 4 and negative 1/10, I should have a hole in this graph. At negative 4 and where's negative? Way over here. I'm like 1, 2, 3, 4. So this point right here, again, let me just edit my graph a little bit. Somewhere here between 0 and negative 1, that's where negative 10th is, at an x value of negative 4. So that point is a hole in my graph. So again, I'm going to just label it because it's not really clear on my graph where that's supposed to be, and there it is. So we're graphing the simplified function and then just including the coordinates for the hole. Since that restriction is reduced out, it doesn't create the vertical asymptote, but we still want to account for it. Okay, now while you're practicing, remember you can use Desmos to verify your work. You won't get it when you take your quiz, but it's helpful to see when you're practicing. So let me just show you what happens in Desmos, like for this example 3. Don't want to type your simplified function in there because you want to make sure that you did the whole thing right. So type your original function in. So I'm going to put problem 3 in. On the top of the fraction was 2x squared minus 11x. What in the world am I doing? Minus 11x and then plus 15 on the bottom of my fraction and x minus 3. And it knows what to do, so it should make the line. Now, it does not automatically make the hole in the graph, but you can still confirm it. So if you put your finger along, like on the graph, and you can move like the cursor along the graph, and what's going to happen is when you get to an x value, oh, I can't see what I'm doing here, an x value of 3, where we put the hole in the graph, it's going to say it's undefined. So it won't explicitly make the hole in the graph, but you can still verify that it's undefined there. Now notice it says undefined. You would still have to be able to compute the y value that goes with that x value. Okay, but again, you can use this to sort of verify what you're doing. So hopefully, again, this is good enough to get you going, and hopefully this looks familiar, feels familiar from college algebra. But if you need some extra help, by all means, reach out, let me know. Until next time, take care.